Hey everybody. So we're going to use the inverse function theorem again to look at the derivatives of the inverse trig functions. In particular, I'm going to show how we can use it to find it for cosine inverse, and then I'll give you the rest of them. They're found in similar ways. But let's remember cosine inverse, how that works first. Cosine, right, all our trig functions, but cosine, right, is a function that we input an angle and we output the cosine of that angle, right? If you think back to your unit circle definition, right, it's the x coordinate on the unit circle when you have that angle in the standard location, all that stuff about counterclockwise, positive, negative, all those things, right? So the inverse reverses that. We take a value, a number that's the cosine of some angle, and it tells us which angle it was, right? However, there's a little bit of there's some complication here. Let's look at the graph of cosine. So here I have a little piece of cosine, right? So the y values, right, these are the outputs. So the x values are the inputs. If I input an angle, it will tell me the cosine of that angle. So for instance, let's put, here's the line y equals 1/2, right? So if I look at x, if the angle was pi over 3, I see the cosine of that angle is 1/2, right? That's why I put in y equals 1/2. Those are the output values. But notice there are at least 3 places where this is true. And in fact, there's infinite places. We know this graph just keeps going on forever. So a second ago, when I said the inverse cosine tells us which angle has the particular cosine we're asking for. So in this case, if I said, what's the inverse cosine of what of 1/2, I'm saying which angle, when you put that angle into cosine, gives you the value 1/2. Well, here I see at least 3 choices, and we know there's infinite choices. How can the inverse function understand that, right? This is the idea that functions, to have an inverse, must be injective. They must be 1-to-1. Meaning that for every output, there's only one input that leads there. And clearly cosine doesn't have that. So the way we fix this is we only look at a piece of the cosine function. We'll look at this piece right here, right? So when we say cosine inverse tells us which angle has the value for cosine that was given, there's a little caveat to that. It's which angle between 0 and pi, right? So this graph begins at 0 and ends. Oh, I forgot to put equals there. That's why it's telling me undefined, and ends at pi, right? So there's 0, 1. Here's pi, -1, right? So now for each output of cosine, right, between -1 and 1. We only go through those once, right? You can see this graph starts at 1 and goes down to -1. And so it only hits each value in between there once. And so we don't have this problem of which possible angle. If you're looking for an angle outside of this, you have to do some work, right? If you end up getting what the cosine is 0 and you get, or the inverse cosine of 0 is pi over 2, but you didn't want an angle between 0 and pi, maybe you wanted one way out there, you have to do a little bit of work to figure out how that corresponds, right? But we can use the values in here to extrapolate to any piece of the cosine function, okay? So that's how we even have an inverse cosine. We do this for all the trig functions. We take different intervals, different little pieces to define the inverse on. So here's what the inverse looks like. Remember, it's a reflection, graphically, it's a reflection over the line y equals x. And so you can see that that blue line does appear to be a reflection, right? Where the red line hits it, so does the blue line. And you can see it's the same kind of shape reflected over that line. So there's our inverse cosine function. And if we glance at this graph, one thing I'm noticing, I'm thinking ahead that it looks like, if I imagine the tangent lines to this, they all appear to be sloping down, right? This thing seems to be clearly decreasing the whole time. So that might just be a little thing I hold in the back of my head, that whatever I get should be something that's always negative, it looks like, right? If it's not, I better double check what I've been thinking, because looking at this, it looks like the values are negative. All right. So with that in mind, let's go back to our problem. and see how we can work at this, okay? So we want to get this derivative of the inverse cosine function. So let's start with let's give it a name. Let's let g of x equal cosine inverse of x, right? This is the inverse of f of x equals cosine of x on the interval 0 to pi, right? That was what I was just talking about there. It's only an inverse of a piece of the cosine function, not the whole thing, okay? So we know that g prime of x, or the derivative of cosine inverse of x, by the inverse function theorem is going to be, so remember, g, again, just like I did in the last video, this is f inverse. G is f inverse. I'm just writing it as g to make the notation a little more distinct, but we can apply the inverse function theorem and say that this derivative is going to be 1 over f prime of g of x. Well, f, remember, in this case is cosine. Its derivative is negative sine. But instead of doing of x, we're doing of g of x. So we're doing negative sine of cosine inverse of x. Okay. Now, this doesn't look good because we're defining the derivative of cosine inverse in a pretty complicated way, right? This is not wrong. It's true what we have written here, but it's a little bit, it seems a bit convoluted. It turns out that this thing in the denominator, and I'll show you how in just a moment, it turns out negative sine of cosine inverse of x is equal to the square root of 1 minus x squared. So sine of cosine inverse of x is the same as 1 minus the square root of 1 minus x squared. And then we have that negative out front. And maybe I'm just going to put the negative in front of this whole thing. So we'll show how that works in just a second. But I do want to note a couple things. First of all, we're taking the positive square root here, which means this square root is always positive, and we've got a negative out front. This derivative is always negative, and we just saw that in the graph. That was our expectation. The other thing to note is that when x is equal to 1, this thing doesn't exist, right? Or negative 1, sorry. And the problem at negative 1, right, because negative 1 would also give us 1. At negative 1, the problem is, right, this is the inverse of this function. If you think of the graph of cosine, this is a minimum on that graph. This is where the curve goes down and starts to curve back up. I don't know why it just zoomed out on me a little. That's a place where the tangent line is horizontal. It's 0, right, which is part of the inverse function theorem. We don't have a derivative there, and we can see why in this picture there is a vertical tangent there, if you will. And so in the problem at hand, we see a 0 in the denominator that we can't evaluate. And over here we have a similar kind of issue. There would be a horizontal tangent there as well, where we're at 1, 0. And so in those two ends, we don't have the derivative, but everywhere in between, we can define it using this inverse function theorem, okay? All right, so now let's show how I found that, what did I have? I'm gonna not worry about the negative. We wanna show that sine of cosine inverse of x is equal to the square root of 1 minus x squared. Okay, so here's what we want to do. Remember, if we have cosine inverse of x, it spits out an angle, right? And it spits out an angle. Let's write this way: an angle between 0 and pi. right? That's what this does. And what it means is the cosine of that angle is equal to x, right? That's the meaning of the inverse, right? If cosine inverse of x is theta, then cosine of theta is x. So let's look at a little diagram of the unit circle. So here's our x and y axis. I'm just going to try to draw the top half. Just hoping it would draw a circle for me. Maybe if I draw the whole circle, it'll pretty it up. All right, so there's our circle, more or less centered. All right, so I really only care about the top half right here. So what does this mean? If we have an angle theta, all right, so we put it in our standard position. This initial side is there. This is the unit circle, so this distance between these two dots on the side of this angle is always going to be 1. This point, remember, this is the way we define cosine is that the x coordinate of this point is cosine theta, the y coordinate is sine of theta, which means this distance here is x, right, is the x coordinate. And this distance right here is sine of theta, but we can also think of it using the Pythagorean theorem that this distance is going to be 1 minus x squared. All right, this is sine of theta. So that's the y coordinate here. If we have x here, this must be y. The y coordinate must be 1 minus x squared. In other words, sine, well, let's do two things. Notice if I take x squared plus 1 minus x squared squared, this is the Pythagorean theorem on this little triangle I've drawn here. This gives me x squared plus 1 minus x squared equals 1, or 1 equals 1. Okay, so that just sort of shows where that came from. Doesn't sort of show, it shows where that came from. Also notice from this, I'm saying that sine of theta is equal to 1 minus x squared. But what was sine of theta? What was theta? Theta is what we named the cosine inverse. It's just the angle that it gave us. So that's telling us that the sine of the cosine inverse of x, excuse me, is equal to 1 minus x squared, right? So the little trail that we can follow through this function is we give cosine inverse a distance, really. When we think about the unit circle, it tells us how far out on the x-axis we went. And it's saying what angle puts us this far out on the unit circle when we put, arrange the angle, the angle where we have it at the origin and all that stuff. And then cosine inverse says, oh, that's an angle of such and such, whatever, pi over 3, 2.793, whatever radians, right? So we get an angle, and then we say, all right, but now how far up is that angle on the unit circle, or how far up is the intersection point? Sine gives us the y coordinate. So we started with a horizontal distance, and we said, what angle got us this horizontal distance? And then we said, all right, if we have that angle, what's the vertical distance, right? That's the series of questions we're taking as we go through this cosine inverse to sine. And then from this simple picture, we see we can go straight from here was our horizontal distance. We use the inverse to get theta, and then we can see what the vertical distance is. And then we're asking about the vertical distance. And this will work for all the angles from 0 to pi, right? I could draw the same picture over here. If I've got this as my theta, then this distance becomes x. It doesn't matter that it's negative because we're going to be squaring things, and the sine part of it will still be positive. That's why we always have this positive square root, because we're only on the top half of the circle. Okay, and so there we have it. There is the way that we constructed this square root of 1 minus x squared. And so now we have a nice derivative, a nice-ish derivative of the inverse cosine function. So let's write that down. We have the derivative of cosine inverse of x is equal to -1 over 1 minus x squared. You can do a similar exercise to get the derivative of the sine inverse, only it doesn't have the negative, right? So I'll leave these as things people can work through. All of these are found in similar ways. There's our three main ones, and these are the ones that come up the most. Maybe this one as well, the cotangent. Negative 1 plus x squared. You don't see these two as often, although I suppose that could just be in my experience. There might be places out there in the scientific world where these come up often, but I haven't worked in those places. Cosecant, and end up with just the negative of this. And so there are 6 derivatives for the inverse trig functions, okay? Some of the utility of these we will see in when we get to integral calculus in the next series, where if you look at these, especially these first 4, there are lots of things that end up with functions that look kind of like these, 1 plus x squared in a denominator or a square root like this. And having these derivatives will be useful to us when we're doing the work for integral calculus, but we'll get there. For now, they are good derivatives to have. And let's just do one example where we combine it with something else. Let's, for instance, take the derivative of the inverse sine of x cubed plus 1. Okay, so what we need to do is realize that we've got now a chain rule. All right, the outer function I have the derivative for now is 1 over the square root of 1 minus x squared, right? I didn't show you this one, but it's similar to deriving the cosine one. G prime of x, we use our power rule. And so we know that this is just sine inverse of x cubed plus 1 is simply the composition of these two functions I just wrote down. And so we know how to take their derivative with the chain rule. F prime g of x, g prime of x. So f prime is 1 over the square root of 1 minus x squared, but we're not putting x into this function, we're putting g of x, so it's going to be 1 minus x cubed plus 1 squared times g prime of x, which is 3x squared. Okay, and you could write it this way. If you're really inclined, you could expand that thing in there. I'm not going to. I'm going to leave it. I'm going to leave it just like this, I think. Let's do some simplification. It looks like there might be some nice things working out. It's never horrible to practice. So this is a perfectly good derivative right here. This is even this was a perfectly good way to write this derivative. Let's look at this thing inside though. Maybe there's something neat that will happen. This 1 minus x cubed plus 1 squared is 1 minus x to the 6th plus 2x cubed plus 1, which is going to be negative x to the 6th plus 2x minus 2x cubed minus 2x cubed. And oh, I see. Yeah, the domain of this is a little bit tricky. So you have to figure out where this thing's going to be positive. We won't worry about that right now. We could also factor out a negative x squared, and then this will look like x to the 4th plus 2x. So if we wanted to, we can put that in here, and we'd have 3x squared over, we'll have an x squared inside a square root. We can pull that out as the absolute value of x, and then what's left inside is negative x to the 4th plus 2x. All right, so obviously this only works when that x to the fourth plus 2x is negative, because then the negative makes it positive if you take the square root. So anyways, this is not super important to have done this simplification. I just felt like algebra is always something we can benefit from looking at again. The bigger lesson here is taking the derivative of the inverse trig functions, and then in this case, combining them with the chain rule. Let's do one more. Let's do one with the product rule. Let's take a look at the derivative of x squared cosine inverse of x. So let's just do this one without writing out everything. The derivative of x squared is 2x cosine inverse of x. And then we leave the first function alone and take the derivative of cosine inverse is negative 1 over 1 minus x squared. Right. So just again, no big revelation there other than they combine in all the ways we want them to. We took the first function, we took its derivative and then left it alone. And the second function, we left it alone, then took its derivative here. So the product rule, chain rule, all of our rules still apply with these new derivatives. Okay, that is it for this one. Thank you, everybody. I will see you next time.